A very good morning to one and all present here. As we step into day 6 of our faculty development program and quantum computing with the theme of quantum workforce creation, we are delighted to welcome two eminent resource persons today. First, we have Mr. Seshir S. Kaushik, a quantum engineer at QPI AI Industries Private Limited, a postgraduate from IIT Jodhpur. He specializes in quantum algorithms, software optimization, and translating theoretical quantum concepts into practical applications. At QPI AI, he plays a key role in driving innovation and scalable quantum solutions in quantum technologies. A warm welcome to you, sir. Joining him, Mr. Venkat Pavan Bandaru, AI and quantum specialist at QPI AI. He holds a master's degree in electrical engineering from West Virginia University and brings diverse expertise spanning AI, ML, deep learning, and also quantum applications. With prior academic and industry associations, his work includes projects in NLP, computer vision, computational biology, and generative AI. Most welcome you, sir. We are privileged to have both of them with us today and look forward to their insights and shaping a strong quantum workforce for the future. Thank you, sir. You may start your session.
Hi, thank you for the introduction. So it was good. Before starting, so I'll just tell you the schedule of today. So what will be happening is based on our understanding, all the theoretical algorithm knowledge has been provided to you already. So we'll be showing you the implementations of it. So just a glimpse of the theoretical knowledge, and you will be applying them on the any of the SDKs or something that we are aware of. So today we'll be using AWS Bracket. I mean, irrespective of what kind of SDK, mostly we'll be writing the same circuits and all. So you don't have to worry about what SDK we are using. It's all the same logical circuits, but written in different SDKs. So the first session will be on Deutsch and Deutsch Joshna. The second half will be on Groover's and QFT algorithm. So we'll be implementing it, and we'll also be demonstrating the notebook for you. And later after, as a part of the quiz, we'll be providing you the notebooks itself. And you can run it and use different logics there itself, and you can test it on that. So there's nothing much. That is all the overall schedule. Just for the clarification, was Deutsch and Deutsch Joshna's theory completely clear? Was it already covered in the previous sessions? Similar to Groover's and QFT? Hello? Hello, Aman. Am I audible? Is my voice audible? Yeah.
Sir, you are
Okay.
audible, sir.
I just want a clarification whether both Deutsch and Deutsch Jostna, Groover and QFT, was it theoretically covered in the previous session? So that we can directly start with the implementation. Because based on the schedule, I'm aware that the quantum algorithm is what's covered, so I'm not specifically aware of it. Okay, so yeah, if someone is asking to revise it, anyhow, I'll be covering some theoretical aspects, then only I will go to the implementation. Okay, so let's start. So as you all know, Deutsch algorithm was a very first or the foundational algorithm that came into existence in terms of quantum modeling. So this is a very first algorithm that came into existence. So I'll just brief you out the problem and the solution so that you'll have an understanding of it. So let us talk about the setting of a Deutsch problem itself. See, the Deutsch problem is very simple. There's one promise solution for that. One is if a function f of x is given, mapping from 0 of 1 to mapping of 0 of 1, we're not considering n on n now. This is just a Deutsch problem, not the advanced version. So in this first promise, it's just a mapping function from 0, 1 to 0, 1. So irrespective of what the f is, f you can consider is as a black box. It's an oracle which is not aware what kind of functionality it is having. But the only objective of f is that it guarantees the function to be a balance. Given any function, It will be either a balanced function or a constant function. So that is a promise and a guarantee of a Deutsch problem. So our objective of this algorithm is to determine whether the given function f is a balanced one or a constant. It will be either one of them. So we need to determine it based on what are the conditions and all, or the oracle conditions that we'll be putting up, we'll be determining it. So this is a very simple promise. So based on that, you can see the left part. So the cursor is visible, right? So this part, there are four different functions. So which is f0 to f of x. So in the very first function, if you observe that the condition is given whatever the input x, f of x should always map to 0, irrespective of whatever the input that we are providing, whether it is 0 or 1, it is always mapping to 0. Similarly, in the second condition, which is f of 1, irrespective of whatever the input is, 0 or 1, it is always mapping to 1. And similarly, in the third one, if you generalize it, whatever the inputs are, f of 0 or f of 1, it will always be equal. So f of 0 XOR of f of 1 will always give you 0, because if you consider the XOR operation, 0 XOR of 0 and 1 XOR of 1 will always give you 0. And 1 XOR of 0 and 0 XOR of 1 will give you 1. So based on that, we have generalized it as if a particular condition of a constant function is, it's f of 0 XOR plus f of 1 will always be 0. So this is the generalized condition for a constant function. Similarly, if you go for the f of x and f of x bar, so these are the last three and fourth condition. So if you see that it is f of x is always mapping to x. So that means the input is mapped to the output. So whatever the input is, which is 0, it is mapping to 0. And whatever the input, which is 1, it is mapping to 1. So this is the third condition, which is f of x. And similarly, if you go for the last condition, which is f of x bar. So if you see that there's an inverse of it. So if it is f of x is actually mapping to the x bar. So whatever the input is, if it is 0, there's an XOR operation. So it is 1. Similarly, if input is 1, it is mapping to 0. So these are the four different conditions that you're seeing. The first two are corresponding to the constant function. The second two are corresponding to the balance function. So in this, if you want to generalize it using the XOR condition, like I told you, when whatever the inputs are, f of 0 or f of 1, it is always mapping to the 1, the XOR operation. So this is the entire Deutsch problems setup. So now these are the conditions we have. Based on these conditions, we need to determine the function f, either as a constant function or as a balanced function. So for this, the only thing is this generalized forms that we have written there, right? The XOR conditions. Only that is required. Based on those conditions, we can actually determine it. So since this is a general problem, so this can be solved using two different methods, which is it has a both classical approach as well as a quantum approach. So if you consider the classical approach, I will just, as you understand the Deutsch problem, our objective is just to verify whether a function f is balanced or a constant function. So if you take a classical approach, what happens there is, if f of x is actually mapped to the f of 0 or 1. So what I'm talking about is a complexity, query complexity here. So what we need in a classical sort of a Deutsch problem is, we need one query to determine whether it is f of 0 is mapping to 0 or f of 0 is mapping to 1. So we are only dealing with 1 now. Our input is 0. So taking our input as 0, we're seeing what is a mapping for that. So there are two conditions, which is f of 0 could be 0, f of 0 could be 1 also. So for that, we need one query just to check it. Now there's another input when f of x is equals to 1. So when x is equals to 1, what will be the mapping function? So in that, we need a second query. So if you consider this just a pseudo algorithm there, for the first query, f of 0 is equals to 0, you need one query. So there are two different variations, which is f of 1 is equals to 0 or f of 1 is equals to 1. So just for these cases, you need one query plus another query just to determine it. So for this case, you need two different queries in the classical case. One for f of x is equals to 0, second for f of x is equals to 1. Now, our problem is, since we already have a existing classical solution, so what is the requirement for the quantum solution? So in the same perspective, we need to do some sort of novelty. We need to show some advantage towards it. So what is an advantage is the query complexity. We are reducing the query complexity. So what was the maximum query required in classical solution was 2 query. Now in quantum, what we are doing is we have reduced it to, we are saying that we only need 1 query now. So how that is possible, we'll be talking later. So this is a kind of novelty that we have brought, the advantage, the quantum advantage that has brought. So if you consider the oracle, it is just a complementary unitary function. So or a matrix in terms of linear algebra, which consists of some variable f of x. So that is just a mapping function that we are doing. So if you consider this equation, when we are starting from x comma y, which is your input, and if it is mapped to the x comma y XOR of f of x. So our y will be mapped to y XOR of f of x. So this is the mapping condition that our oracle is going to do. And this is just a linear representation, the matrix representation. And there are major conditions in order to, before calling a particular matrix or a unitary matrix to be a unitary or a quantum unitary matrix, there are 3 conditions it needs to be followed. That is, I hope it is already covered. One is if u of x is actually our matrix, unitary matrix or oracle, it needs to be a Hermitian matrix. And the second condition is it should be a unitary matrix. Then only you can call that as a unitary vector. The third case is it should determine, in whatever the cases of f of x, the u of f should determine the determining mapping function, whether it is balanced or constant. So that is the major properties of the unitary gates. So whatever the unitaries that you produce, it needs to follow those. And the rest of those things are just the oracles and all. So the same general oracle that you saw here, I'll be representing them into 4 different categories because we talked about 4 different conditions.
Minus j omega epsilon by h squared into j and rho h into sin n phi dash into n into a
I think
into
mic is on. Yeah, okay. So, I was talking about 4 different conditions, right? So for each and every condition, we need to construct a oracle. So oracle is nothing but the circuits. This is just a general form. Now I'll be just dropping down into the smaller circuits here. So our very first case was whatever the inputs are, it should be mapped to 0. So in the same condition, what we need to do is you don't need anything. You just need to apply a identity gate because it does nothing. So what it happens is whatever the input is, if f of x is equals to 0, it is the y dash. That is our interested thing, right? So that should always be mapping to 0 because now if we start from x and y as 0, 0, we'll be getting 0, 0 itself because it's just unitary gates, right? Whatever we are getting, you are getting that. So when x is equals to 0, y dash will be 0. When x is equals to 1, y dash will also be 0 because our y is 0 here. So nothing is happening there. So irrespective of whatever the input that x is having, y dash will always be 0. So this is following our first condition. Now our second condition was f of x should always be mapping to 1. So in this case, if you see when x is equals to 0, y dash will be 1 because we started from 0, y is equals to 0. Now we applied x gate, it has turned to 1. So the y dash is 1. Now if x is equals to 1, then also there is a y is equals to 0 and then there is x gate, so it is turning into 1. So when x is equals to 0, y dash was 1 and x is equals to 1, y dash is still 1. So this is matching our second condition. And these 2 conditions, as I told you, these 2 are the constant condition, constant function conditions. Now, when we are talking about these 2, if you see f of x is equals to x, then this means that our input should match with the output. So in the same case, what we are trying to do here is when x is equals to 0, we are saying that y dash is still remaining 0. Because if you see here, there's a CX gate. So what is the property of a CX gate is whenever the the controlled bit is once, then only it is activated. If it is in one state or excited state, then only it is activated and the target state is applied with some NOT gate. Or since we are talking about C naught, X gate is applied. So based on this, if you see that when X is equals to 0, there is no activation of the C naught function, so it remains as 0 itself. So Y dash is 0. So when X is equals to 0, Y dash is 0. Now when X is equals to 1, the controlled bit is activated and a C naught gate is applied on the target bit. So when X is equals to 1, Y bar is also 1. So this is following the same condition, right? When whatever the input is, the output is of the same function. So this is the third case. In the fourth case, it's just reverse, vice versa. That is the reason we are introducing a X gate here. So when X is equals to 0, no activation of C naught, and Y dash will also be 0. Similarly, when X is equals to 1, there will be a C naught activation. So as X gate will be activated. When Y is equals to 0, it will be turned into 1. And again, there's a X gate, it will be turned into 0. So when X was 0, Y dash was 1. When X is 1, Y dash is 0. So this is the reverse process and the truth table that you can see here. So what I'm trying to say is for 4 different conditions, we have written 4 different oracles. So we'll be using the same oracles for our implementation for 4 different cases. So we'll be defining the oracle, we'll be predefining the oracle. Based on that, we'll call the oracle, whatever the conditions there, and then we'll test whether it is performing the proper determination or not using only one query. So the one query thing that I told you there was, I'm not going to go into the detailed implementation since it is a brief out. So whatever the Deutsch algorithm or whatever the algorithms that we talk about in quantum, it all stands on 3 different pillars. So one is quantum parallelism, one is phase effect, and one is the interference. So if you see, this is Hadamard, the Hadamard transforms that we are performing here. These are the ones which are responsible for the quantum parallelism effect. So once the parallelism effect is done, once all the possible states have been encoded in the superposition state, then there's a phase effect that will be performing. So there, due to the phase effect, which is like -1 power e power I pi. So based on that phase effect, we'll be defining whether we are getting a constant function or a balanced function. So those steps you can actually see in the phi2 level. So +1 or -1. +1 or -1. So there are 2 different possibilities for constant and 2 different possibilities for the balance function. So based on that, again, what we'll do, we will apply a interference pattern there. So when there is already a superposition state, and on top of that, we are applying another Hadamard only on the first qubit. So then an interference pattern will be formed. So based on that, there will be 2 different sort of interferences. One is like constructive and destructive. So if we are observing a constructive sort of interference, then it is something we can categorize them as a constant function. Similarly, if it is having a destructive kind of an interference, we can call that as a balance function. So these 3, using these 3, can actually determine it. And one more important thing that you need to notice here is we are applying Hadamard on the first qubit and then we are only measuring the first one. So the reason is that means that we are only doing one query there. We are not measuring both the qubits to determine it. So based on one measurement, we determine whether the function f of x or f is actually a constant or a balanced function. So based on these conditions, 5 of 3 conditions. So this is all about the Deutsch. And when we talk about Deutsch-Jostna algorithm, it is just a generalized form for n number of bits. Initially, we only talked about 0 and 1. Now we are talking about 0 in terms of n inputs. So in this case, we are doing the same technique. We are not following any other things. But the thing is, since we are doing Hadamard transforms on n number of bits, there'll be a multiple superposition states. For that reason, you can observe the mathematical condition here. So it is summation of x comma 0 of 1, which is mapping to n. And also the phase that you can see, which is -1 f of x of 0. And again, we are applying a Hadamard on the 1 state. So this is like a minus state. So we are not doing anything with it because we are only measuring the first qubit or the first register. So this is just for the registers. And one more important thing here is like how we were actually based on the kind of phase that we are getting, based on a kind of constructive or a destructive interference that we were getting in a Deutsch, we are determining whether it is a constant or a balanced function. In here, what we do is, if you see there are two different conditions here. When f of x is equals to constant, when x is equals to 1, and also when f of x is equals to constant when x is equals to 0, there are two cases. If you see there is a -1, the phase is -1, which is just a 180-degree phase shift when the constant is mapped to 1. Similarly, it will be +1 when the f of x is a constant function mapping to 0. So these two cases just within the constant function, if you observe this, that based on that, you can actually say whether it is a balanced function or a constant function. In the balanced case, what it is happening is the probability is completely 0. If you see that it is mapping to 0 amplitude. So that means that you are not getting a all 0 state. But in these two cases, you're getting completely 0 state. So 0 state, what do I mean is you'll be getting a string of 0, 0, 0, 0, 0 in the constant cases. But if at all you find something like 0, 1, 0 or 0, 0, 1, 0 based on whatever the input that you're taking, that means it is a balanced function. It is no more a constant function. So for that, what we do is we just calculate a no zero probability. So the no zero probability in the balanced case will be absolutely 0. It will never be 100%. But in a constant case, it will be 100%. But we need some other category, right, to determine whether it is mapping to 1 or 0. For that, there's another category which is based on the phase. If there's a phase shift, then we can say that it is all mapping to 1. And if there's no phase shift, then we can say that it is all mapping to 0. So these are the 4 different cases in Deutsch-Joule. Initially in the Deutsch, we didn't matter whatever the thing it based on the constructive and destructive interference, we used to clarify it or categorize it. Now this is since a generalized form where we are talking about n number of inputs. These are the categories. We directly take up what is a probability. Based on a probability, we just categorize it. So keeping this in mind, I'll just go through the entire notebook, how this is actually instructed. So, I mean, I previously told you that we'll be using a bracket SDK, right? So, bracket, if someone is not aware, it's actually an SDK, a software development kit dedicated to program a quantum computing algorithms or circuits based on your wish. It is provided by AWS. It's developed by them so that you can access multiple hardwares. Wherever you want to program a particular algorithm or a particular circuit respect to your applications and all, You can perform it, you can program them, and you can also test it on the local simulator that AWS itself is providing. And if you want to render any of the hardwares available from multiple companies, you can also do that using the credit access. So we'll be using AWS Braket today. So it's very simple thing, as I told you, irrespective of whatever the SDKs are, the constructions of the oracles and the circuits are same. So you don't have to worry anything. Only thing is you're changing the way of representing a particular circuits. The name definitions can be different, but the circuits remain same. Because ultimately, what we are targeting when we are running a program on hardware is just a CASM code. So it doesn't matter whatever the SDK that we're using. So just as a prefix, we just have to install the Amazon Braket SDK. So I will be providing the entire notebook to you, so you can also run it in your local Google Colab, or you can download it. You can run them locally. So for that, what you need, you just have to install the Amazon Braket SDK. So once the download is done, you don't need any other dependencies, because all the dependencies that is required is already provided in Amazon Braket. So just have to install that one package. So then you need to install matplotlib. This is just for the visualization purpose. So once you import that, you need to import circuits, because this is a module where you can define a circuits there. Whatever the circuit that you're defining based on the algorithms or the oracles that you're designing, you need a module for that. So this is the circuit module. And then for all the gates and all, you need to import the gate module. And like I told you, if at all you're interested in simulating them on any of the simulators that is provided by AWS itself, you need a device or a simulator. So what you need to do is you just have to import a local simulator. Now, based on that, if you remember, I told about 4 different oracles respective to 4 different functions. So for the same thing, I've just written a definition function, which is like constant oracle. So this is the one which is dealing with constant oracles. So if you go back, there were 2 different cases when f of x is completely mapping to 0 and f of x is completely mapping to 1. So in the same logic, if you see, I told you that you need a circuit module, right? So now we had imported the circuit model and we are defining it as circ.circuit. And this is just a range of n qubits. Based on whatever the number of inputs that you are interested, you can just import them. And we are giving some random outputs, initializing it. So this is the main oracle that we are targeting for. So if the case is, if any of the random output or the mapping output is only mapping to 0, then we do nothing. Because I told you in the very first function, you don't need to do anything. You just have to apply a identity gates, combinations of identity gates. Similarly, in the second case, if the output mapping is equal to 1, so then what you need to do, you just have to apply a X gate in the second register. So that is what you're doing here. So this is just a else statement. If the output function is equals to 0, apply nothing. You just have to apply the identity gates. It does nothing. Similarly, if it is mapping to 1, you just have to apply X gate, so that whatever the input is, it should give you the output as 1 only. So this is our constant oracle. And also this is just a validation, because it needs to be within the greater than 1 case, because with one circuit, with 1 qubit, you can't construct a oracle of a Deutsch algorithm, because you need 2 different gates. Similarly, we have written a balanced oracle. So in this case, what we told, there are 2 different cases, if you recall, which is f of x is mapping to x and f of x is mapping to x bar. So which means whatever the input is, the output will also be equal. In the other case, whatever the input it will be reverse. So keeping the same thing in the mind, we define the module circuit as circ. And in here, if our mapping function is equal to 1, then we are applying a X gate here. Initially, the X gate we'll be applying, and then we'll be applying a CX gate. So this is a control as our qubit in the range of n bits. So whatever the input that you are providing, if it is 2 or 3, so the control and target will be initiated in the unitary way, in the linear pattern. So then finally there's an X gate. Because I told you when there's an inverse pattern, when X is equals to 0, the Y bar will be 1. So for that case, after the C0, we need a X gate. So for that case, we are also defining the final X gate here. So this is our finalized oracle balance function for the balance function case. Similarly, this is just a subroutine. This is for construction of the first Hadamard transform, and this for the constructions of the interference pattern. So what we do is we just return a function as Deutsch-Jostner circuit, and we are just importing all the self functions. So this is our circuit module. We are just adding our circuit where we had defined the Deutsch oracle, and we are just calculating the probability of it. And this is just to extract the bit string and plot it. Now what we are doing here is we have defined our initial n number of qubit as 4 different qubits. So whatever the functions that we are defined, now we are only interested in the constant oracle. So we just call the constant oracle and we have initiated it as 4. So this is our circuit for the constant case, because it's just the combinations of identity gates and the X gate. And similarly, if at all we are interested in a balanced circuit, our n number of qubit was 4, we just call it, and this is the balanced function that looks like. This is the oracle for 4 different qubit. Now what we do, we just have to extract a probability. So we just measure one of these combinations and we need to extract a probability. So there'll be a probability distribution. So based on that, for that reason, what we need to do is we need to measure them and we need to simulate them. So for the same case, in the previous one, we had already imported the local simulator. So we just call it back. We just call it as a device. And then our task is to extract the probability. A number of shots, we have provided it as 10,000. So for the 10,000 times, it just measures the same oracle, the above oracle, and it provides a kind of a distribution, probability distribution. And we just extract the same probability distribution and then we plot it. So using the plot bit string. So if you observe it, it is all equal to 1, 1, 1, 1, 1. Because we initially took the balanced oracle. This is the oracle that we took, balanced oracle. If you see, I've defined it as balanced oracle. So in this case, if you see, we are getting a bit string as 1, 1, 1, 1, 1. So that means that it is no more a constant function. Because if at all it was a constant function, it would have been a bit string of zeros. So this is just a validation thing. So similarly, if you're interested, you can call the constant function. So you can call the constant function. You can run this and you can provide it to the local simulator. And if you map it up, you'll be getting a probability which is all mapped to 0, 0, 0, 0. So that means it is within just one query, you're just measuring one of the outputs, one of the inputs. So if within just one query, you are able to determine that you're actually the given f of x function is a constant function or a balanced function. So this was just done on a particular simulator. Now there's also another thing. So this was a result that was actually executed on the hardware. So if you see, the ideal thing was we need to expect 1, 1, 1, 1, 1, 1. So it should be 100% matching to 1, 1, 1, 1 according to the local simulator result. Now here we are finding multiple distributions. So this means that hardware has imbibed with some of the errors by itself. So due to this error, you can see multiple distributions. It is also going to 0, 0, 0, 0, 0, 1, 1, 0, 1. So there's a sort of a constant distribution. But ultimately, what is our target is we need to find the probability of no zero solutions, right? So in this, since we are dealing with the balanced function, so irrespective of whatever it is, we are still expecting 0, 0, 1 solutions and 0, 1, 0 solutions. So this means that it is perfectly categorizing it as a balanced function. If was a case of constant function, then it would have mapped 100% to 0, 0, 0. So the only difference is due to some error, you can expect a kind of plots like this, but whatever the kind of simulation, whatever the algorithm that you'll be doing, so everyone would ask you to try it on a simulator, and then you can cross verify the same results on the hardware. So this is the entire implementation. This entire notebook will be provided to you. So you can also change the variations of constant functions and or the balance functions, and you can observe them. And you can also run it on the hardware and you can cross verify the solutions. So when if the same kind of session will be followed with the next algorithm, which would be like a groover. He will also be giving you the brief description of whatever the Oracle constructions that will be happening in groover, and then also in the QFT. So based on that, in the second task, he will be explaining you the notebook. If you have any sort of doubts in running the notebooks or the theoretical aspects of Deutsch, you can ask me.
Sir, is there any specific hardware is available to test this dice algorithm and dice algorithm?
Yeah, if you actually go to the AWS bracket, they provide a multiple hardware access. So if you're interested to render IBM hardware or IonQ hardware, that based on your interest, you just have to pay some credits. So based on that, you can do the solutions. And I believe that some of the credits are provided you as a free, so you can use that also for smaller circuits and all. But most of the time, the simulators are obviously free for you.
Participants, any queries? Please ask. Thank you, Shishir. Pawan, next resource person, Venkat Pawan, he's going to join. Participants, please wait.
Hi, shall we start?
Yes.
Is my screen visible? Like,
Yes, visible.
yeah, okay. So, I think he started with Deutsch. So, right, he started with Deutsch, right? So, I'll try to give you a broad overview to Deutsch. Then, I mean, I'll try to walk you through overall things. Like, he started about algorithms, right? So, I'll try to walk you through what are the algorithms present and overview of entire thing. So you can complete overview I'll try to provide. So oh, let's start. So yeah. So I'll start with the broad timeline for the quantum. So how it was started and everything. Then I'll give you a broad overview of what's happening and what's there. Then I'll try to continue with a one algorithm as has taken or one algorithm which is to be told or something. So just a second. So you have this thing, right? Uh, you can see the screen, right? Yeah. So
Yes.
this is the broad timeline for the quantum computing. So you can see it is very modern. So the thing is, you'll be using. I'll try to walk you through the things needed also, so you can have it. See, there is a linear algebra. So which is the base? I mean, which you have. Then you have this classical physics and modern physics. Why this is very modern is, and why there is limited in quantum is, it's modern physics. So it started very recent. Unlike classical Newton physics and all, it started. I mean, its boom started. I mean, even though philosophy is there, its boom started around 1900. So it was little recent thing. And you can see the Bell inequality was conceptualized in 1964. Then this was the birth in 1970. So then this was the first thing where Feynman has proposed his quantum compute. Then, I mean, it's very. I mean, you can say it's very latest in. I mean, it's very 1981 saw the proposal. It's not even uh, any framework or something. So then you can see the how the quantum cryptography at 1984 started. Then this was Deutsch's universal quantum computer. Then this is the actually 1990s was the major turning point where Shores showed a way to solve the large factorization. Like he solved a factorizing a large number through quantum principles, which was usually which classical compute takes a huge amount of time, like I mean some thousands or millions years, which Shores tried to solve it through quantum principles in very simpler, very small amount of time. So this is where the I mean actually the push for quantum compute has started. I mean this is where the research speeden up, and then you can see the Grovers. Grovers is like, I think here in the first session, Shishir has talked about Deutsch and Deutsch-Joche. So these two are trying to show the quantum advantage or quantum supremacy, how using the quantum thing you can reduce the time complexity or runtime complexity and everything. So this is where you can see these two give a solid push, the Grovers and Shores. I mean, Grovers is on, I mean, unstructured data. So Shores is about factorizing a large number. So you can see, I'll try to show you a notebook for Grovers as well, like how uh, comparing classical search with uh, Grover search or quantum search. Then you'll understand the key motivation, like how the time complexity reduces. I mean, this tries to reduce the time complexity quadratically. Like, I mean, the thing would be pi by 4 to n when linear search takes n. We'll come to see this as well. So then this is where in 2000's first trap ion quantum computer tried, but this is superconducting qubit actually pushed it. So this was the major year where Google showed its quantum supremacy. And now the race is going on like with qubits. So these two also, the Grovers and Shores, even though they are theoretically fine, but they require a lot of qubits. So which is right now, that's why the scope is limited for these two. And hybrid algorithms like QAOA and all are in picture majorly, optimization algorithms and all, then Grovers and Shores, pure quantum algorithms. Because, and especially these two, and the advantage is shown with the increase in qubits and increase in qubits as well, especially with respect to Grovers. So that's why this hardware part is limited. So all over. But at, I mean, for simpler qubits, you can see the advantage as well. But with larger qubits, you can see how advantageous quantum can be over classical. So this can be your broad timeline. And then you have your, I mean, slowly, the one more thing for quantum push is have your machine learning and AI. So ML and AI needs are very data dependent. They are heavy data dependent, and they have to perform lot of I mean they need a lot of hardwares like GPU and all to process the information, like the innovations like clustering GPUs or processing batch wise and stochastic. Using stochastic principles and all, they are trying to come up with, but these require, they are very data dependent, and every, like for example, right from e-commerce search to everything, e-commerce search to every simple application has a lot of, they are very heavy data dependent, and these require a lot of compute. And the classical systems, the time complexity and all is huge. Even the innovation for transformer model is over sequence to sequence model, which the push has started, where the RNNs or deep learning models, their runtime complexity is very high because they have to process the thing word by word. Transformer architecture in attention mechanism, you try to parallelly process, right? So even then with transformer architecture, the machine takes a lot of time, GPUs and all. So then comes, you can use the quantum principles and you can use QPUs. You can, with increase in qubits and all, you can process the information very speedily and efficiently. So this is your broad overview of the thing which I wanted to tell. So then, so this is, I'm not going to talk about the lab setup and all. So, or about IR stack or something. So now I can. So before this, I'll try to show you what are the available software development kits available in the market. Then we can see one advantage of, we can start with classical, how comparing classical and quantum through Groovers. Then we can see the later on, we can see the later developments as well. So you can see. So in IBM, you have these kind of software SDKs, we call SDKs. So you have these things, Qiskit, and Google has Cirq. These are also SDKs. So you need not worry much about, these are used to run your algorithm, because now I'm going to show you a notebook. So I thought I'll just walk you through them. So then you have this TensorFlow Quantum, this from Google. Then Microsoft, you have QPlus and Azure. So most heavily used are Qiskit and Bracket. PennyLane also. PennyLane is very good. So these are having, the other things are Quest, Cubo, and Project Q and everything, hardware agnostic. But most of them are following the same, and most of them have a similar software base or development base and everything. So it's like developing SDKs for gates and everything. So now, and one more brief overview I'll give you is, so I'll start with what kind of quantum we are also using. So you can see. So the thing which we are, see, it's every. For example, you have a. I'll just give you a small motivation. So you have gates like AND, OR, NOR. AND, OR, XOR, etc. These, you will be, people who are doing DSA and all might also be aware. They'll be using this gate heavily for bit manipulation kind of tasks and all. Bit manipulation and everything. So these are called universal gates, basically. So, and you make circuits with them. You make DLD kind of things with them. For example, you are adding two numbers. So 1, 0, 0. So if 2 are 0, you are the answer should be 0. So it's like you're based on your, you'll be using OR gate or something for your this kind of operation. Then if it's 1, 0, you have to get 1. So you'll be making a half adder or full adder to get the tasks done in the classical thing. So similarly in quantum also, it's always gate based models. Like you have gates like, you'll be forming a circuit based on your gates. So I'm not going completely into the details of it. So even the quantum is gate-based model. I mean, you have a lot of gates like single qubit gate, 2 qubit gate, and all. So in single, so you'll be having C naught, everything. You'll have rotational gates, everything. I mean, it's very gate-dependent model. So it is called. So I mean, we are trying to build a circuit-based models. So these are the things which people are working on. I mean, available and heavily working on. So it's like everything, a circuit is built and you'll be trying to take it from there. So now I'll try to show you a example. Just give me a second. I'll try to share you a notebook. 1 second. So you can see it here, right? Like you can see this notebook, right? So you can see now we are trying to compare Groover search algorithm with classical linear search. So you guys able to follow?
Yes, it's like that.
Yeah. So yeah. So now this is like comparing classical. We are trying to compare classical. I mean, it's visible also, right? This screen. Yeah. The notebook, is it visible?
Yes, it's visible.
Yeah. Okay. So we are trying to. Okay. I'm presenting the wrong thing. So let me present you this one. So is the notebook visible now? The Colab notebook visible now?
Yes.
Yeah. So yes. Okay. So you can see it. So now I'm trying to compare the classical, the working of classical with regard in quantum. So this is what I'm trying to do. So this I'm trying to show you with a linear search, or I'm trying to show you with a Groover's. So it's nothing. I mean, I'm not going to the details or technicalities of it, but I'm just trying. This is for a comparison perspective, so you can try to understand. I'll try to brief you both. So the Groover's is an algorithm used for searching. Like it is very helpful in searching unstructured data. So this has a lot of applications, but need a lot of qubits to show actual practical uses. But theoretically, it is proven, and you can understand the technique later. But let's see a comparison. So for now, we'll try to have a so. So it's like now you can see this is about Groover's. So now you have your linear search. So what does linear search means? See this Groover. Let me talk about linear search first. So now imagine I have a database with 10,000 records of data. So I have 10,000 rows. I want to find a particular ID. I mean, there is a column called ID. For example, I have this thing, 3-column data with 10,000 rows, where there is an ID, and where there is a some sort of pay and other here. So, for example, I have to find the ID which is at 5,000th row. I mean, I have given an ID which is my target, and I have to find it based on the ID. So what will I do? I have an ID. In linear search, I'll try to take the ID and I'll try to have, this is my target. Target is equal to, you can think ID. ID 1, I mean, you can take it as ID. Okay, for example, I'll take ID 786. You take it as ID 786. So I'm trying to check whether this is present in the 10,000 record data or not. So now I'll use this 786 and I'll compare with the first one, whether it might be 654 or something. So second row, I'll come to second row, again I'll compare, third row, I'll compare. In a sense, I have around, if the record is at 5,000 place, I have to compare it 5,000 times, right? If it's in first place, I have to just compare one time. So I'll write a loop where I have to compare it. So I'll get based on it. So my time complexity will be, if it is at last at 999 place, I have to iterate it over this time. So in worst case scenario, it will be 10,000, will be O of n. In average times, I might find it half the place, so it might be around 5,000. And in best case scenario, I might find my record at first place, so it will be 1. So this is broadly my linear search would be, how my linear search would be. So I'm taking 1 and I'm comparing it with multiple things. So now when compared to Groover, as it is not a classical algorithm, so as it is a quantum-based algorithm, so how it works is, you have a qubit system depending on number of qubits. For example, I have 8 record data. I'll write it as 2 power 3 and I'll take a 3 qubit system and I'll start comparing them simultaneously. I'll start comparing the bits simultaneously. And there is one more thing also. It's one thing, and you can do even multi-column search simultaneously as well using Groovers. So multi-column search or these kind of operations can be done easily. So now let's see how it is being done. So for this, I have been using Amazon Braket, Amazon as SDK. So I'll be walking you through it. So I was installing Amazon Braket here, the very first step. So then I was importing the necessary tools which are required for my visualization or something. I mean, for my visualization in math and everything. So these are my things which needed from ITER tools and all. So then I'm generating a synthetic database here. You can see. So for 1 bit, you have 2 possibilities, 0 and 1. For 2 bit, you have 4. For 3 bit, you have 8 possibilities. So we consider the database n is equal to 2 power n items. So I'll take it as 2 power n, where each item is indexed by n bit string. For example, n is equal to 3. So I'm doing it this way. So you can see it here. I have generated a synthetic database with 8 items. So you can see 3-bit database here. I have generated 8 items, 000, 001, 010, 011, 100, 101, 110, 111. So there are 8 items, i.e. 7 binary numbers are there. So now I am trying to search it. So now you can see with regarding linear search, how it is. So time complexity to run this would be 1. I mean, best case first 1 comparison if target is first item. Worst case is n comparison, and average case is n by 2. So the time complexity usually is O of n. So now I'm initializing it, and now I'm comparing it with each of the things. I mean, I'm having comparisons here. So in my linear search, it gives me, for example, I'm searching for this 101, which is at 6th position. So at and index 5, it is at index 5 and it is at 6th position. So I'm just trying to compare. So it is at 6th position. So you have to compare it. I mean, for index 5, you can have it around 6 comparisons should be done. For this, so this is how linearly we search. This is the code for linear search. Then you can have your comparison with quantum. You can try to see how quantum provides an advantage over it. So searching for 101 in this. So classical, it is at position 5, 6 comparison needed. So we do optimal Groover iterations. Unlike classical search, which stops when found, quantum search is probabilistic, right? So we need to run the quantum algorithm for exactly right number of steps to minimize our chances for success. So as I said, there is a quadratic time reduction. So your time complexity would be this much. So you need to just run this many iterations instead of running O of n. For example, you have 8. So you have to run 8 comparisons or 6 comparisons. Instead, we'll try to run, if it is 6 comparisons which you are doing, you'll be doing pi by 4 root 6. I mean, somewhere near to pi by 4 root 6 iterations you'll be doing, and you'll be getting your answer in such limited iterations as only. So you can see it where you can see the clear explanation. N is equal to n 2 power n. So we'll be rounding it to nearest integer. So you know the pi value. So this is with regarding groovers. So I mean, you can have the geometric intuition as well. You are starting at a point 45 degrees from the target, and each iteration is rotating by 2 by root n radians. So you need to rotate pi by 2 radians for each target. You can see number of qubits 1, database size would be 2. You can see the comparison here as well. So let me write this. You can see the one qubit database size is 2, as it is 2 power n. So you can see 2 power 1, 2 items in the database. So you have classical, worst case you have to find 2 in Groovers 1. I mean, you can, in the morning there was also Deutsch Joshi, right? How you can compare it with 1, whether to find the function is balanced or constant function. You try to do it in 1 iteration, right? So it's this way. Then there is a quantum speed up of 2x here. Then if you have 2 qubits, you have your 4th size database, and in classical you need 4 iterations. In quantum you might be reading in Grover optimization, you might read only 1, and your speed up is 4. For 3 you have 8, which we are doing right now, and you have your classical 8, and worst is Grover is 2, and you have your 4x speed up. But here you can see with the growth of qubits, I mean database size and qubits, you can see classical 16, Grover iteration is 3. You can see here, right? 1, 2 doesn't make, but here 1, 0, 2, 4 comparisons, classical worst, and you have to see, you can see 21, 25 times. Here it is 41 times speed up, quantum speed up, right? And here you can see where these many iterations are needed. 1 lakh 048,576. In Groover you need just 804. You can see how advantageous is its speed up is 1304x times. So from here, I mean, that's how your with the growth of your qubits, you can see for 20 qubits itself, your search can be done this efficiently, right? So you can solve the problem this efficiently, like the time complexity is very much reduced. I mean, with 20 qubits itself, you can have this speed up. So this is what quantum advantage, and it becomes more dramatic. So this is how you compare classical with quantum. So this is the thing for your function for optimal iterations. It is nothing. The code is just hard coded. So you can see it for 1 qubit and all. So for 7 qubit, you are doing just 8 iterations. So this is how. So now it's as I said, everything is circuit based model. Circuit based, you'll try to initiate qubits either 0, q0, q1, and you'll try to form a circuit. So for superposition, to have the principle of superposition and entanglement, you'll have this Hadamard, and then you'll try to. So this is how, I mean, you're bringing with superposition the 3 pillars. Then you'll have this oracle, which is a black box function. You need not worry about oracle function if you're not being taught or something. You can just think it as a black box function. I mean, in Deutsch or Deutsch-Joshi also, there is a use of oracle. So it's similar to it. So you can see it. So the oracle, it is flipping the qubit generally. So what oracle does is, it is preparing the qubit, and it has a phase flip, and it restores back to its original basis as well. So usually represent with this UF of state X. I mean, usually you'll write, you have this Q0, Q1, have your H, and you have your oracle, and this is how circuit building goes. And again, you'll apply reverse, and then you'll have your diffusion and all. So this is how usually circuit is built for every quantum algorithm. So you can see, you're applying the diffusion so that you're amplifying your target. It does inversion about the mean. So it reflects all the amplitudes above their average value. So this is what it does. You need not worry about if you're not following what oracle or diffusion or something is. It's like basically I'm explaining the Grover circuit builder. So it's just like you're forming a circuit to solve this search and reduce the time complexity. This is the broad overview. That's it. So this is the steps to start. You have your initiating start. You're having creating a superposition. Then you'll be having your oracle. Then you have your diffusion. This is how you'll be doing your Grover. Then you'll be repeating each iteration, and you'll be measuring it. Everything at the end, you have to measure the classical to quantum. So this is a broad thing about quantum. So I'm sorry. So this is a broad explanation of Grover. So you can see the explanation for code as well. So I'm having the key elements of the code also. I'm targeting. My target is this. So I'm building a 3 qubit system because it's 2 power n. So 2 cube, 8 elements in the database. So now I'm creating a 3 qubit. So the code also has this much only. The code also follows the same. Now I'm initializing the superposition. I'm using Amazon Bracket for building a circuit. Now I'm constructing a circuit. So you can see the 3 qubit gate. This is why I'm trying to say there are single qubit, 2 qubit, and Toffoli for 3 qubit and all. So now you have a 3 qubit Toffoli gate, which is controlled by the first 2 qubit, that toggles the third, and encapsulated between Hadamard gate to implement a phase flip. So this is Oracle construction, you can take it as a black box for now. So which performs a specific function according to your need, our need. So you are applying what is in is, we can see it later. Then you have your diffusion, then you have your Grover's iteration and measurement. So broadly you can see it, the steps are this way. So you are initiating, you are trying to superpose. So this is done using Hadamard. Then you have your Oracle function. Then you have your diffusion, Grover iteration. So now you have your measurement. So measurement is, I mean, you are trying to collect the rate. You're trying to collect, I mean, how many, I mean, based on number of shots. I mean, we'll see what it is. I mean, I mean, the code is run on simulator or local simulator and all based on 1,000 shots. I mean, 1,000 for 1,000 repetitions and all. You'll try to measure, like basically you'll try to compare the success rate of quantum and all. That's it, nothing major. Or usually, I mean, otherwise also you have quantum measurement. You're trying to measure it to classical thing, because once the output is in, I mean, quantum measurement is nothing this like. It will be tried to, I mean, usually how to cell is, it will be collapsed to either 0 state or 1 state, and based on this you'll try to have some sort of, then you'll get your classical output. I mean, you'll try to make it classical and you'll measure it. And here you are trying to, in the code, this step is about running on the quantum simulator for 1,000 shots, I mean specific number of shots, and we are measuring the selected rate and all. I mean, measurement follows. This is how the major steps going on. So you can see the Grover search algorithm here. So, I mean, as I said early only, I mean, there is a limitations of qubit for to show its efficiency and all. But you can see the code, you can see how it has if for n qubits, and you can see you are initializing the superposition Oracle, the same steps which are dealt, you are writing in the code as well. You are trying to use the superposition here through H gates, you can see. Then you have your Oracle function which is built. Then you have your diffusion operator. I mean, I'm trying to just explain the code here. So you can see this is first diffusion, then your measurement. You can see how it is going. These are the steps. Then you are having testing you are trying to test the Grover's algorithm for 101. You are trying to find it. You're trying to find. You can see here, iteration 1, database size 8. You have found it in 2 iterations. I mean, I did a bit of hard coding here. That's fine. But you can see for 101, you are able to find it using 2 iterations, where linear search gave you 6, because it's in the fifth index, and as I mean, the indexing starts with 0, 0, 1, 2, 3, 4, 5, 6, 7. I mean, here it is there. So you need to have at least 6 iterations in classical or linear, where in quantum you are able to do with 2 iterations. So that is iteration 1 Oracle plus diffusion, iteration 1. I mean, so that's how, I mean, it is also about also measuring it. You can see the 1,000 shots. So the success rate is 93.5. So this is, these are the measurement results here. So this is a broad comparison of, this is comparing classical with quantum. So you can see 2 iterations and 6, I mean, just to have an overview. So is it clear, or I mean, Any doubts still here or anything you want me to ask here?
Any doubts, participants, please ask.
Is it clear? I mean, so, okay, I'm hoping it's clear. So I'm trying to continue. So, and I mean, you can stop then and there and you can ask your questions. Let me share you the other presentation. So, I mean, this is how, I mean, as I'm saying, it's everything is circuit based model. So this is what a circuit based model is. So you can see, I mean, these qubits are fundamental. So that's how I'm trying to show even in the groovers. I mean, what we try to build is a circuit. So these are the gates and this is how a circuit is built. So this is one thing I'm trying to show you. So in the code as well, we try to build a circuit. I'll try to show you the circuit as well. Circuit things as well in the code, like how each single qubit, 2 qubit and all gates, how are they? I'll try to open a notebook and show it to you. But first thing is we try to compare. I mean, we started with infusion. Then we try to compare classical with quantum. Now we are trying to have this, I mean, what circuit building is, because gates are the building blocks. I mean, gates are the building blocks for circuit. And you can see this is how a circuit is built. So this is how we design all our algorithms. So it's basically a circuit-based model. So you'll be using different kinds of gates, rotational gates and everything to build your circuit. So before going to the current stage and all, I'll try to give you a overview of circuit as well, so that it would be a little holistic understanding. So I'll try to show you the gates as well. Just a second. Okay. So you are able to see this one, right?
Yeah, tutorial notebook, right?
Yeah.
Yes, visible.
Yeah, it's visible, right? So yeah, you can see. I mean, this is done on Qiskit. I mean, I can share you this notebook. I mean, you can run it on your own. So now you can see a single qubit gate. I mean, how gates are implemented on code. I mean, this is just kind of a hands-on for you. So as we are talking about circuits and everything, how circuit is built, I'm trying to just show you, and a block sphere representation of it as well. I mean, I'll just walk you through it, and then we can see the current phases of the quantum and we can wrap it up. Yeah, okay. So, I mean, the common single qubit gates are poly gates, XYZ, poly XYZ, or this is poly NOT gate, and each thing performs a different function. Like one gate flips a qubit, one gate adds rotation to the qubit and all. So you can see, then you have your classical Hadamard, then you have into qubit you have your Hadamard, then you have your Toffoli and all for 3 qubits and all. So now you can see so we can see the poly X gate, and what does it I just mentioned. So how it does, it behaves like classical law simply. So you can see the explanation for it, and if you see, this is the code. I'm not running it now, you can run it, but you can see the gate, it has been already run. So you can see how the application of poly X gate would be on the qubit. You can see this is the circuit diagram usually, and you can see the Bloch-Spear representation for it. Wait, I'll try to run it. If okay, it will be more easier. So I'll just okay. So you can see we installed the Qiskit version. Now I'm just trying to run this. I'm just importing the libraries, the required libraries. I'm running it. Then you have your poly. I mean, I'll run for each X gate. I think you have been taught about these gates earlier as well, the session. So you can see the circuit is built, and now you have your Bloch-Spear representation for it. Now then it's your poly Y. So you can see how poly Y is, and you have your and it performs a phase shift in the Y. So you can see you can see how the poly Y and what it does. So you can run it here, and this is how the poly Y gate circuit representation is, and this is the Bloch-Spear. Then this would be a poly Z, and you can run for poly Z gate, and you can see the representation and how it has. Then this is Hadamard. It creates superposition usually. So because you have your Hadamard matrix as well and everything, so I'm not going to details of each gate, but this is the gate representation. So you can see these are the phase gates ST, so which are commonly used. So these are the its Bloch-Spear representations, and then these are rotation gates. So you have this, and these are simple. Then you can have your 2 qubit gates, C0 and all. So how these are, how base state preparation happens and all. So you can see C0. So the circuit, I mean, these are the results to, depicting, and this would be the C0 gate circuit, 2 qubits. Then you have your control Z. So you can run it, and you can see here, I mean, you have your control Z. This is a Bloch-Spear representation. Then you have your swap, and everything has its own function. When you can read it later as well, if already done, it's good. You might be able to better appreciate or comprehend. If not, it's fine. So this is for swap, and this is for Toffoli. It has 3. It's a 3 qubit, and it's representing 3. You can run it, and you can see the circuit building as well, how it is. So it's Predican gate. Then you have your similarly I have done it. I mean, each one is having its own. So so this is how a circuit is built, and this is for, then you can see for a sample circuit how a code is built. So this is a Bell state and maximum and timing. Bell state, you can see how there are 4 Bell states. You can see phi plus phi minus, psi plus psi minus. So each one goes this way. Each state, each representation. So you can visualize this using this. This is how a circuit building usually happens. So for each state, this is how. So each Bell state has one at the end a specific use case and all, right? So this is how it goes. So this is the circuit representation for 4 states. Then you have the explanation for this code as well. So, and the blocks here. So this is multi-entanglement. You can see, I mean, nothing major here, similar. You can see how the circuit is building for 3-qubit GGH circuit, GHG circuit, I mean. So you can see entanglement here. For this, it is this one, the state vector, and for this here, you can see. So this is how broadly you can see the circuit building for 3 qubit. This would be for 4 qubit, and this would be for 5 qubit. So this is for 4. You can see this for 5. I mean, how circuit building is happening. So you can see it's like you're applying superposition here. Then you have your C naught in the second qubit, Q2, Q3, Q4. You have been taking it, and then you're applying gates, and you're building a circuit. So as I said, it was mostly a circuit-based model. We are trying to build or solve problem. So this circuit-based model forms the base for all the algorithms. So then this is one thing. So this is how a circuit is built and it goes on. So now I'll take an example algorithm like QFT and try to show you how exactly the circuit operates. Just a second. Just a minute. So you can see this one, right? So we'll take this an example and we'll try to, I'll try to walk you through just a minute. Hello. Hello. Okay. 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 It So now I'll try to show you a circuit with the help of one algorithm. I'm sorry. So I'll try to show you with case of one algorithm. So this is quantum Fourier, QFT. I'll just give you a very basic overview. I mean, you need not focus on the algorithm here. You can see about circuit building because this is little advanced algorithm. So going into math part and everything becomes little difficult. So I'll try to just walk you through algorithm. Then you can have an understanding. I mean, I'll just give you a walk you through. Have your DFT, then you have your FFT. So your DFT has a O of n log n, I think, and this has your time complexity of O log n square. It is reducing it. So FFT and QFT is further reducing it. So in DFT and Fourier transform and all, what you do is generally Fourier series is you'll try to analyze a signal from time domain to a frequency domain. So your Fourier series is usually only for periodic signals, limited to periodic signals. So your Fourier transform tries to generalize it, like you'll be trying to apply it to, I mean, what do you say, non-periodic signals as well. non-periodic as well. So here comes then your DFT, discrete Fourier transform, then your fast Fourier transform. So then we are using the Fourier transform or QFT. So it's like you're applying on a qubit. So it's either represented by tilde or it is QFT. So I'm not going into the detailed math part. I'm just telling you what classical, just the overview, and I'll try to show a circuit building. That's it. So that would be my agenda is that. So you can see the classical, and you can see the, as I said, the quantum speed up for this. You can see quantum, you have your n log n2, you have 2 log n square. So it's an exponential speed up. So this is what a 3-qubit circuit looks like. So the application part of QFT will be signal processing, image compression, audio signal, noise cancelling, noise identification, and everything. So this is the broad qubit kind of, how. So for this you have to build a circuit, right? So this is how you build a circuit. You apply H Hadamard, then you have your rotation, then you have your Hadamard, then it goes on. Then you'll be applying inverse Fourier transform to get back to the original state. This is how. So you can see phase encoding, physical intuition is, in the applications are in this usually. Sorry. The applications are in Shor's, quantum, and this thing. So, it is, it transforms periodicity detection. Actually, right? Now I gave you a overview of what Fourier series and what Fourier transform does, and then what DFT and what QFT. So the purpose, so then it tries to transform periodicity detection from exponential classical search to polynomial time computation. So it has very large applications in cryptography and all. So you can see eigenvalue problems in quantum chemistry and it's also basis for many quantum cryptographic protocols. So that's why QFT becomes, the application of why QFT and all is such that, it has huge applications. Now, we use these algorithms to solve few problems. That's how these applications become. Now let's try to understand the circuit building. Basically, the intention is to build a circuit, right? So we'll try to go with it. So this is how math behind QFT, DFT, and then math behind QFT works. Now let's not better go to the math. So that's why I'm skipping, nothing major. So it is actually how, it's a general qubit state here, and then you have your QFT formula. So this is a general qubit state, you can see, and you have your, now we are applying it on a QFT. Generally, you'll try to, QFT in the sense, we'll try to apply Hadamard only. So here you'll get for 0 state, you'll be getting positive, and for 1 state, you'll be getting negative. It's like applying Hadamard. So it's like you can take it as tilde. It's for 0 state, it's a tilde. 0 tilde will be 1 by root 2. 0 plus 1. Applying QFT. So QFT over 1 would be 1 by root 2. State 0 minus 1. This is it. This is the basis transform. Generally, okay, I'll try to tell you. You might have Laplace transform and everything, right? You might have Laplace transform. You might have different transform functions. Basically, it's like building a kernel. You'll be seeing the QFT equation. It's simple. The math behind is building a kernel. Have a kernel function right there. So it's like it will be, for example, you have your X qubit, and now you're trying to have your function in terms of X comma Y, and then you have your Y qubit, which is your output. So this would be your kernel. So that thing which it does is transform. It transforms. The basic advantages, for example, you can take this as this way, Y kernel and all, Laplace transforms and all. So you have your data. For example, I'll try to give you apart from math, a regular practical intuition. So I'm separating it with, I mean, many people aware of AI and ML would be aware of it. So I have this, and which is linearly separable. This is one kind of data. This is other kind of data. So for example, yeah, I'll represent it with L1. So this is the data point. This is these are linearly separable with a line. It's fine. Now, if my data is this way, it becomes difficult for me to separate it. Non-linear separation. So what I'll do is I'll use a kernel function which transforms my two-dimensional data to higher dimensional, where my data becomes this, and my data becomes this, and I can separate it through a plane instead of a line. So this is how usually the kernel functions and all the applications would be. That's why I said I'm not going to math part of it. Usually you'll have this kernel function also here. It might be if you are doing Laplace, you have Laplace. I mean, you have some different kind of function and all. So you can see the math function here. Math formula as well for this. You can see this is the major equation. Yeah, this is the mathematical structure. So this is the math, and this is J is your input, this will be your output, and this would be your JK. It's your kernel kind of function. You can see unitary transform or something. So this is how what applying QFT mathematically means this. Now we are trying to solve for 1 qubit, and then we are trying to do it. I mean, sorry for bothering you with all the math part, because the intention is not now, but I just want to make it clear how it is being done. So then I'm not going to this part. So this is how you have to do. I mean, this is how applying on one, how the bases are transformed. It's like converting from computational basis. I mean, from one basis to other basis, like what a Fourier transform does is. So this is the thing. So this has how the basis transform works. So you here your Hadamard application for QFT usually. So for 0, this is what I'm trying to say. You get this one plus this is on 1, because the Hadamard function is this, you can see. So this is how the circuit generally has. So then you have, it's for 2 qubit system, your application of QFT would be this. I mean, this is for your 2 qubit, and the formula would be same. In 2 qubit state, you'll have this one. And this is with, for example, I just try to explain it with 1 2 qubit thing. You can see how it is represented. Then you are applying control R2, then you are applying hertz to second, and this is circuit building. So I mean, then you have this unitary transformation. The properties are, it is unitary in transform, like you multiply its complex conjugate with Q. I mean, the original one you'll get an I, and this is periodic in frequency, because I mean you're trying to find periodicities in the quantum states. Well, just don't bother about the properties and all the part of it. I mean, this is for 3 qubit, and this is how a circuit is built. You are applying Hadamard, then you have your rotation, then again on 2nd qubit you have your Hadamard, then you have your on the 3rd, then you have your swap. I mean, the steps actually, circuit steps, you H on Q0, then control R2 and R3. Then you have H on Q1, then control R2. Then you have your H on Q2. And then you're swapping Q0 and Q2. Bit reversal you are doing, then you are getting this. Then you'll apply inverse QFT as well. So this is the broad steps. So this is how it is going on. Then you have your, after applying, you get this. So this is inverse QFT formula, and you have this key property as well, and you'll try to check it. So this is overall, this is inverse QFT circuit. So everything is a circuit-based model. So this is what. So I mean, you can see it with an example. You have applying qubit over 001, then you got this, then you are applying inverse qubit, you got this, then you are verifying it with this. So this is usually a step. So the properties and the circuit complexity and all you'll be measuring. Total depth, how many gates are required, and all. So this is how classical DFT of n square, classical FFT of n log n, QFT6 quantum gets exponential speed up. So I'll give you an overview of the session now. So we started with a brief timeline and intuition for quantum. So in the intuition timeline, then we try to have a classical versus quantum comparison through prover. Then we have seen circuits, how circuit building, I mean gates and circuits in the code. Then we try to look an example algorithm like QFT, how circuit is built. We did not go into detailed math and all. This is a broad overview. And yeah, and one more thing I would like to add, as there is also a mention about quantum workforce and all. So you can find, I mean, as it is going and AI is in boom, and till and when transformers came into picture, people were not, or attention mechanism and all, or GPUs, people used to feel this is a very research oriented. For example, till GPT was in market, I mean GPT 3.5, NLP was restricted to, people used to feel NLP was academic and research oriented thing. So, but once this was thing there, I mean, in industry level, people used to work mostly on vision problems and all, fraud detection and all, ML problems and all. But once this in picture, now Gen AI got its boost, and NLP now became mainstream. Everyone is looking for AI engineer and AI dominant roles and all. So this is one major thing now as well. So from 2019, when Google came up with its quantum supremacy or quantum advantage, the boom has actually started and it's growing exponentially. So you'll find here things, I mean, the job roles at SDK level, everything is increasing, even hardware part and all. So with growth of more qubits, I mean, with scaling up to more qubits, I think, and already like the optimization algorithms are in place, like QAOA and optimization part. For example, our company is also QPy Opt platform is performing well, and we are serving many clients. So I think it's gaining a lot of traction, and there is a need for skilled people as well. And the classical advantage here is everyone is new and everyone is at very beginning. So, and the concepts are limited, and there is a lot of scope for exploitation, and everyone is new and everyone is starting their race here only. I mean, people good with stats and math and all. So, I mean, it's level playing field. So for everyone all over the world, and it's booming. And I mean, I think it's able to solve many optimization problems and all. Now I think we are also serving many clients and all as the need increased. So as we have our own hardware as well. So uh, yeah, with this I would like to sum up the session. So any doubts and all you can ask me. So any doubts? I mean, is it clear? Is it helpful at least? I mean, uh, any binomial coefficients? I couldn't understand that out now. You can little elaborate it. Yeah, I mean, there is an algorithm Fourier transform. Actually, I mean, you can work on it. The thing we do Fourier transform is already Fourier transform has a lot more applications, right? Like, I mean, it has a so I mean, it has I mean, lot of I mean, in signal processing and all, we try to analyze the signals, right? In general Fourier transform, you have your AC component, DC component and all. And binomial has its own, you have your A0 and all. That when we do our regular Fourier transform and you have your AC component, DC component, you'll try to analyze the signal or you'll try to find noise and all. So that's one application. Then as it has some application and all, then we are trying to use QFT. I mean, you can you can use it using Qiskit and all. Everything is actually given. I mean, it's in the notebook. So you can. That's the very first slide. I mean, after the timeline I have showed, right? Like you have a Qiskit of IBM. Then you have your Amazon Bracket. These are all the software development kits. You just need to import them in the Colab or your local. You can just try to pip install and you can work on it. Yeah, we can apply. So yeah, we can noise cancellation and all. You can apply. There are use cases for it. I mean, you can try to solve them, and once the code is ready, I mean, you can take up a problem and try to see for it. I mean, usually how the Fourier transform works, you can have, but mostly in quantum part, you use it for cryptography and protocols as well. So you can use it for, I mean, image compression and all these things. Yeah, you can try looking the applications. Yeah, I mean, random number generations, one way you can do for, yeah, I think it gives you true randomness as well if you are doing with hardware. So yes, it might be also good. I mean, good thing. Yeah, you can use it for QRNG because in QRNG, I mean, using quantum, you cannot trace back to the original, and that's how the cryptography base forms for, like, because the quantum advantages, it can provide you a true randomness. Then you can have your evaluation metrics like Shannon entropy, and also that you can try to come up with some sort of QRNG. But I think usually we do it other way, QRNG. I haven't used QFT, but I mean, you can try actually. That would not be a. I have to look into it how it can be applied exactly, but on a regular student level or something, you can try generating 2-qubit system. Then you can 2-3 qubit system. Then you can. One thing is quantum cryptography and all entanglement. I mean, if you understand entanglement, it's like this thing now. Like you will, for example, I mean, quantum teleportation and all. There are things like quantum teleportation and all these things where you'll have your you'll initiate the qubit, and the information is converted to classical, and from classical you'll try to generate the original information, and the original information is destroyed in between. That is one way. I mean, if you go through the teleportation mechanism, you'll understand how well it can be used for network security or cryptography part, like exactly. For example, you can see that, I mean, teleportation circuit that has that's majorly one base for, to say in the cryptography part. One more thing is you can generate true randomness. For example, OTP generation or these kind of things are there. I have a pattern. I know which cannot be traced back actually, but you can see right how it factorizes huge number in very small amount of time, like which might take years for a classical thing to solve. It solves in a lesser amount of time. And that might not be the exact thing for quantum cryptography. Let me tell you like this, the security purpose, like if you're generating a random number, for example, I have an OTP and I have a pattern. I mean, how much ever difficult to crack the pattern is it has a pattern actually to say, and it might be cracked some way or the other, or the randomness can be cracked some way or the other. Through quantum, what it is, it is always in a state. It is in either 0 state or 1 state. I mean, it might be either 0 or 1. It's a probabilistic model, right? So it is difficult to predict what next number would be, because it's always in 0 or 1 and all. So it is very probabilistic and it is difficult to find. So it has a lot of applications. For example, QKD and all, how LS receives signal from Bob and all, the famous application. So if I'm sending my qubit to Bob, that's what teleportation again comes into place. So and you can read about quantum key distribution and also how the cryptography works, and the true randomness is one. Yeah. So okay, let me show you a teleportation circuit which might help you understand. Just a second. A quiz, I don't know. Are we supposed to share a quiz? I'll talk with ma'am and let you know.
Yes, we will share the quiz evening around 7 o'clock.
Huh? What, man? I did not understand. Can you repeat? So you can see I'm sharing you a teleportation thing. So it's through bracket itself. You can see LS has a quantum bit. You can see it here. So now LS is sending a qubit. I mean, it generally involves in sending a qubit through classical bit. So LS want to send, LS has this bit and he wants to send it to Bob. So what does he say is, he shares the maximum entangled state between them, and they have one of the qubits with them, and LS has the unknown qubit as well. They have one of the qubits and which are entangled, and LS has unknown qubit which he wants to send. So she'll initiate this way, and after this she'll try to only send the classical part. From classical part, Bob tries to get back the information. So you can see it. LS will, I mean, it's gate construction. You need not worry about that. The conceptual part is this usually. So LS, I mean, depending on this 0001, he tries to get back. So basically this would be the circuit. So you can see, and he'll try to have density matrix and he'll try to get, and the teleportation is after a point, the qubit is destroyed and you have the classical bit, and classical bit you'll try to generate your quantum information which LS has sent. So then you have your quantum key distribution and all. So this would be a thing in cryptography and all. So
sir, yeah, sir, it was nice, sir. I understood. One more query, sir. That symmetric, asymmetric, we used to say, no, sir, in that cryptographic algorithm, generally network security. The same way, anything like that, sir, public, private, like that, we can follow up in the quantum cryptography, or entanglement only it will be followed, sir.
I mean, there are again different protocols, man, like BP, NP, and all. So you have to study. I mean, cryptography as such. I mean, the quantum communication part has a lot of protocols. I mean, these are the basic principles, and there will be having a lot of protocols as you.
Okay, sir. Okay, sir. Thank you. Thanks for the information. It was very nice, sir. Thank you.
So,
if possible, yeah, sir. If possible, can you share your mail ID, sir? If possible.
Yeah, it's pawan.d@qpi.tech. Can I type in the chat? Should do-
Yes, sir. Yes, please, sir. Yes, please.
Yeah, you can see it, right? So, any further doubts or something you want? So, if no more doubts, I can leave. I'll try to.
Participants, any doubts? Please unmute yourself and ask. Okay, I sincerely thank Sushir and Venkat Pavan for the insightful sessions on Dice-Josh algorithm and Grover's algorithm. At the same time, Pavan explained Amazon SDK, so how to implement it using Jupyter Notebook. So as well as the hands-on guidance with many circuits. So your expertise and the clear explanation made these advanced topics much easier to understand and apply. Thank you, Pawan, and thank you, Sushir.
Thanks, ma'am.
Thank you very much.
So, yeah, I can drop, right?
Yes.